So good afternoon, everybody, and welcome to today's live webinar. I'm Simon Patton. I'm the CEO of EMQN, and I'm going to be joined by my regular co-chair, Professor Sandi Deans from GenQA. And today we're going to be talking about, or giving you an overview of the results from the 2022 Liquid Biopsy EQA scheme for lung cancer. I must point out this is a non-promotional webinar being organised and funded by AstraZeneca. Okay, next slide, please. So a couple of housekeeping duties before we get started on today's webinar. We've automatically muted all your microphones to avoid any background noise. We are recording this webinar, so we will be making it available on the GenQA and EMQN YouTube channels. Probably, it normally takes about 2 to 3 weeks before we put it up there, but we will, of course, let you know when it's available, so you can watch it at your leisure, share it with your colleagues, etc., for the shared learning that comes from it. And as per all of our webinars, we think that audience participation makes these webinars successful. So we really do like and encourage you to submit questions and answers, well, questions to us for answering at the end of the webinar. So there will be a slot at the end where you can submit questions. Obviously, please do feel free to submit them in advance. That would help me and Sandi to be able to know what's coming up. But please use the Q&A session to actually record or log your questions for us. Next slide, please. So your feedback also helps to contribute to our webinar program and process. So we really do value your feedback. And hopefully you think that these webinars provide good quality, high quality training for you and your colleagues. And that's what we hope you will use them for. So after the webinar, you'll get an email from AstraZeneca with a short link, or a link, should I say, to a short feedback survey. It should only take a couple of minutes of your time to fill it in, but we do really recommend that you do so. Your feedback really makes a difference to us and lets us improve our performance next time around as well. So please do complete it. Next slide, please. So just our disclosures. There we go. Next slide, please. And I'm going to hand over to my colleague, Sandi, who's going to give the introduction. Over to you, Sandi.
Lovely. Thank you, Simon. Welcome, everyone. So we're delighted to be able to give you an overview of the 2022, as Simon said, Liquid Biopsy EQA for lung cancer. So next slide, please. So it's quite important to outline what the objectives of this EQA was for, so you can understand what we've achieved and what the outcomes are in summary. So really we wanted to assess the testing accuracy and the clinical reporting of EGFR variants, and that was a mandatory part of the EQA. But we're aware that other laboratories test for different targets. So we know the most commonly tested for secondary target is KRAS currently. So we included that into this assessment, and that was optional. So for laboratories who do test for KRAS routinely from your liquid biopsy samples, then this was exercise that you could submit the results for. We didn't want laboratories to stand up any KRAS testing if that was not their normal procedure. So really the objective is to help make improvements through using a combination of the assessment, which is the scoring of your EQA returns, and feedback, and really giving some expert and advisory comments back to your individual laboratory so you can tailor your feedback and response and reactions from the EQA. And that's done through the individual laboratory reports and also an overarching EQA summary report that highlights all the issues that's been raised and also provides the validated test results, etc. So the format of the EQA is very similar to all the other assessments that we provide through EMQN and GenQA. So it's the accessibility of the participating labs to correctly determine the genotype in the ctDNA lung cancer sample that we were provided. Then go on to interpret the results in response to that specific clinical referral that is provided along with the samples in a clear format. We were looking for the correct use of internationally accepted standard nomenclature, in other words, HGVS. And also it's important that we know the report is linked to a specific patient or clinical test. So it's about the identification is correct, appropriate and accurate with regards to patient and sample information and identifiers on that report. So next slide, please. It's great to see we've got such global reach now with this EQA in particular, and we had participation in this EQA scheme from 52 different countries, with China being the most frequently participating, followed closely behind by Italy and Spain. But as I say there, you can see that we're across the different continents, and it's great to see that we have engagement across the world. Next slide, please. So it's really important that we make sure that we know what's included in our EQA samples before we send them out to participants. So, and that's the only way that we were able to actually assess the genotyping accuracy. So we commissioned 3 custom manufactured artificial plasma samples from SenseID at 80 nanograms per mil in 3 mils of artificial plasma. And really this was to reflect the samples that come in the real world from patients into your laboratories for testing. The manufacturer had previously validated the levels of DNA in their samples using digital droplet PCR, but we wanted to make sure that the samples that we received prior to distribution was what we expected them to be. And also we'd be able to give a reportable result after transportation through the EQA process. So the genotype of each of the EQA samples was validated, as always, independently, blinded, so they didn't know the expected results, in 3 different laboratories. So we had a range of different techniques because, again, we want to make sure that they're fit for purpose, regardless of which assay that you use in your laboratory. So we looked at the Roche-Cobas test, the digital droplet PCR using custom biorad primers, and also NGS, which was an in-house panel, which was capture-based specifically for ctDNA testing. We then also wanted the laboratories, as I say, to then interpret the results that they obtained in regard to the scenarios that were supplied. Next slide, please. Again, the value of EQA and participation is about the data that we can collect, so we can actually see what the testing methodologies are currently in use in the real world rather than what we're expecting. So here you can see that the Roche-Cobas EGFR mutation test version 2 is by far the most commonly used assay. Then we see the ddPCR and then the MockCDX EGFR mutation assay. And then if we move to the next slide, please, you can see here the emergence of laboratory developed NGS testing themselves. And I think it'll be interesting to track to see how that changes over the next few years with the CE-IVD regulations coming into play. So next slide, please. So again, we're looking at the methodologies. We're aware that testing for circulating tumor DNA within the background of normal cell-free DNA requires the use of methods that are a lot more sensitive than those that we routinely use for DNA extracted from solid FFPE tissue or fresh tissue. And that's due to this low amount of the circulating tumor DNA present in the plasma sample. So that's why it's more technically challenging for laboratories to perform this testing. And we know that these variants can be down to as low as 0.01% or 0.1%, and that's the assay that we're looking for testing. So it's not necessarily the sensitivity for the testing that's important, but we also have to layer on top of that with when these results are reported and whether they're clinically actionable within your local practice going forward. So we know some methods, this sensitivity, such as ddPCR, may not be able to simultaneously detect different clinically relevance. So it's really important to choose a method around about a 1% detection. So you've got to compromise between the balance of the scope of the assay to be tested, so what you actually need to be testing for, and then the sensitivity of the assay used. So it's very difficult to assess exactly which assay you should be using in your own clinical practice and balance that with the expectations from your service users. So Simon, I'm going to hand over to you now to go through the first of our 3 cases with the feedback and the learnings from this EQA run. Thank you.
Thank you, Sandi. And just to emphasize that last point that Sandi made about assay performance, I mean, one of the really good ways of being able to do some external testing of your sample validation process is the EQA samples, when we're providing you with a range of different samples with variants with known genotype. And particularly in the context of what we're doing here, we're using artificial samples, so we've got very tightly defined criteria for variant allele frequency. And again, it provides a really good way for you to be able to assess your performance. But as Sandi showed in the previous slides, you can see there's a huge range of different assays being used by different laboratories here. So, I mean, what we, a spoiler alert, we haven't detected any systematic errors with different assays, but you can see the huge variety we have that we have to cover and assess in the process. So on to case one. So I'm going to go through case one, what we expected, what we found, and some common shared learning from it. So case one was a male patient from whom a blood sample had been taken. So the patient had previously presented with shortness of breath and had been diagnosed after investigation with metastatic lung adenocarcinoma. And due to the shortage of tumor tissue, molecular testing for using plasma had been requested to determine future treatment options. So in this case, we were requesting EGFR testing and KRAS as optional, and we were expecting laboratories to detect an EGFR variant, so C2582T2A, which is P.L861Q, if I'm right, in my amino acid interpretations, at 6%. And no KRAS variant was present in this sample. So an unusual EGFR variant, but not that uncommon. So we found, well, 9 laboratories made genotyping errors, so that's 3.1% of the tests that were done for this case, and a further 3 laboratories made interpretation errors, or 1% of the testing for this case. Next slide, please. So if we look at just a breakdown of the types of errors that were made by laboratories, you can see the vast majority of errors made in this case were false positive results. This is the most common type of error we see. So we're seeing a large number of laboratories reporting different KRAS variants, include G12C, but there's also a G12D, an L223I, and a G15D. And also a different EGFR variant. So you can see an L858R in there as well. There was obviously usually a false negative somewhere. There was one false negative result. One laboratory did detect an EGFR variant but reported the wrong EGFR variant. So they, instead of L861Q, they detected L858R. And finally, one laboratory made what we think is probably a sample swap error. So they reported the wrong result for case 1 and for case 3. So they reversed the results itself. We can't tell whether that's a true sample swap, but it's certainly a reporting error anyway. So that's a breakdown of the types of errors we see, and as in common, mostly false positive errors reporting. Next slide, please. There were 3 critical interpretation errors, and so the 3 errors really were associated with the following. So one laboratory suggested chemotherapy as the first-line treatment. Don't forget this referral has been asked about molecular testing, with referral to using TKIs, for example, for testing this patient. So that interpretation was wrong in the context of the clinical referral provided. One laboratory didn't report an EGFR variant because it was outside their scope, and that's absolutely fine. However, they then went on to interpret the result to say that the patients with EGFR resistant mutations in exon 20 may confer resistance to first generation TKIs and have benefit to third generation. Well, this was considered misleading because obviously the context here is slightly different, the variant is slightly different, etc. And finally, one laboratory stated that the presence of a sensitizing L861Q variant in the sample meant the patient had decreased likelihood of obtaining clinical benefit from an EGFR TKI. And again, that's wrong in this context for the reasons I'll talk about now. So we included this variant because it was uncommon. And we know it's not that uncommon, but it certainly is uncommon compared to L858R or the more routinely tested variants in the EGFR. And its response to TKIs is contradictory. When you look at the literature, there's not strong consensus on whether it will or won't respond, or patients will or won't respond. So patients currently do show some sensitivity to TKIs compared to patients with no EGFR variants. and particularly in third generation TKIs. So really it's about ensuring that you communicate that level of uncertainty, if you like, but the fact that the patient may respond as a consequence of having this type of variant. Although obviously it is clear that there is a level of decreased sensitivity compared to, say, some of the more commonly tested variants or occurring variants in EGFR, such as exon 19 deletions or L858R. Next slide, please. Other reasons for common deductions really were, in the cases where laboratories didn't detect or were unable to detect the EGFR variant, primarily due to the scope of the assay they used, there was an overinterpretation of the absence of that variant. You know, as the EGFR wasn't detected, it's too strong to suggest that the patient's unlikely to respond to EGFR TKIs. It's the nature of cfDNA means you cannot be certain that that's the case, and so you have to make sure you include riders to suggest that there is a level of uncertainty in your conclusion associated with that. So that's we really consider that overinterpretation in this context. The other main two reasons for deductions of marks were for not recommending a follow-up tissue biopsy or a repeat sample. Again, really important in this context when you haven't detected the original variant. And finally, failing to provide sufficient information regarding the methodology used or the limitations of the assay. So again, it's really important in the context of when you don't pick up a variant to make sure that the end user knows what the limitations of what you're doing are and the consequence of that for the end result. So again, make sure you include the sufficient information on your assay used and its limitations, etc. Next slide, please. Over to you, Sandi.
Thanks, Simon. So case 2 was another case where it was requesting molecular analysis through a liquid biopsy test. This sample had an EGFR variant in at 3% allelic frequency. This was a del-ins, and a 2% variallelic frequency, which is the T790M, which is the resistance mutation that's well known. And there were no expected pathogenic variants in the KRAS gene that was tested for the 3 exons. Now, we saw a doubling of genotyping errors from case 1 in this case, and also a lower number of interpretation errors, only one of them, which is 0.3%. So next slide, please. Again, a flip side from case 1, where we had predominantly false positive results being reported. Here, the majority of errors were due to false negatives. So either they didn't report the presence of either of the EGFR variants, or they reported the exon 19 deletion, but not the point mutation, or at the flip side, not the point mutation, but they did report the deletion. We also had 2 laboratories who were reporting false positive results. One of them was an incorrect EGFR variant, which was over and above the 2 expected variants that were present, and then even a third extra variant there by the 3rd lab. So really a complete no themes or common issues there, just a completely different way of picking up different variants that weren't actually present in the sample. So next slide, please. When it comes to the interpretation, we were expecting participants to understand that the presence of the resistance mutation, which is the common resistance mutation, indicated that the patient had an increased likelihood of benefiting from 3rd generation EGFR TKIs. There was one critical interpretation error because the laboratory stated that this acquired mutation is predicted to be a sensitizing mutation. This mutation, however, is associated with resistance against all but the 3rd generation TKI. So I think that's really important you understand and define which TKIs that you're actually referring to. There were common deductions. One was about the number of labs interpreting the case as if the patient had not previously been treated with EGFR TKIs, and it was very clear in the clinical case scenario that this was not the first treatment options, that they already had been on a TKI. So it was about interpreting the results within the correct clinical setting. So these were common errors. We also saw the presentation of separate interpretations because of 2 different EGFR gene mutations being detected. And we really want to see an overall interpretation because it is one patient and the variants are not there as standalone on their own. They are present in combination within that patient. So we were really looking for that overall interpretation that summarised all of the findings within that clinical context. So Simon, I think that's all to say for case 2, quite a challenging one, I think. So over to you for case 3 now.
Yep, thank you, Sandy. Yep, I agree. Case 2 was challenging for laboratories. We deliberately set it that way, obviously, to make sure we could pick up that common type of combination of variants in EGFR. So over to case 3. So case 3 was a male presented with a persistent cough and shortness of breath. And imaging had detected a mass on their right upper lobe of their lung. They'd had EBUS sampling, demonstrated a TTF1 positive malignancy, but there was insufficient material for a standard biopsy. So they've been they requested plasma testing to determine future management of and treatment options for the patient. So in this case, we weren't expecting laboratories to find an EGFR variant, but we had included a KRAS variant, so G12C at 4% variant allele frequency. So a slightly different scenario here, trying to look at new and emerging therapies. So the KRAS 12C is a target for that context. The number of errors sort of fits in between the first and second cases. So there were, in terms of laboratories testing this case, so remember it was optional. There were 288 laboratories registered for the scheme. In this test in this case, there were 154 laboratories, which is about, if I do my maths correctly, about 54% of labs tested for KRAS. There were 6 genotyping errors, which represents 4.2% of all the tests undertaken on this case. And there were a further one more interpretation error, or 0.3% of all the tests undertaken on this case. Next slide, please. Okay, so when we break down those genotyping errors, you can see that again, as in case 1, the majority were false positives. There were 3 laboratories that incorrectly reported an EGFR deletion in exon 19. There was 1 laboratory incorrectly reported the presence of a different KRAS variant, so P.A59T, which is obviously incorrect, the wrong variant. And 1 laboratory also reported the presence of an EGFR exon 20 insertion. And finally, the last error was caused by a laboratory we talked about in case 1, mixed up the samples or reported the results wrongly for cases 1 and 3. So we call those a sample swap error with case 1. Okay, next slide, please. Looking at the interpretation errors, so as reported, there was 1 critical interpretation error. So don't forget, this was a sample with no EGFR variant, and the laboratory reported patients with an EGFR gene-resistant mutations in exon 20, so in this case T790M, may confer resistance to first-generation EGFR TKIs, but have benefit to receive third-generation EGFR TKIs. Of course, this case didn't have an EGFR variant in it, and there was a KRAS variant. So we considered that confusing and also misleading for the context of the patient. So this sample contained the G12C variant, and recent phase 2 trials have showed that there is an inhibitor that targets this variant that has good activity in non-small cell lung cancer. And as a consequence of that, the FDA and EMA have already granted approval for use of this drug in patients with non-small cell lung cancer. And phase 3 trials currently ongoing. So we acknowledge that not every laboratory or every context, every national context may have availability to the drugs, this type of drug, but it's coming, and we think it's really important laboratories should be mentioning that on their reports, that there is now available a drug for laboratories who do have or present with this variant in their genotype. So we would and were looking for laboratories to make some sort of context or a report about that in their feedback in their clinical report. Next slide, please. So common deductions for this case. So again, over-interpretation of the absence of the EGFR variant. So it was a KRAS variant. So one laboratory certainly put too much emphasis on that to say that there was unlikely to be a response to second or third generation TKIs. So reinforcing the fact you need to be reading the clinical context and also looking at the genotype you find and drawing conclusions based on the patient data you've got available to you. Other common deductions, just like case one, so laboratories not recommending testing of a tissue biopsy or repeat sample when they didn't detect the original EGFR variant. And finally, again, just like case one, not providing sufficient information on the limitations of the testing methodology used or the assay you actually performed. Next slide, please. I think it's over to you, Sandi.
Thanks, Simon. So those are the three cases that we've sort of done a deep dive in a summary of the findings. When we were looking and preparing for this webinar, Simon and I identified three other areas that we wanted to discuss today. Now, the first of those is about HGVS nomenclature. We're now seeing that this is now used by the majority of laboratories, which is fantastic. It's something that we've been trying to promote over the years because it's incredibly important. We have some standardization now, and particularly when individuals and laboratories are using databases. So we make sure that we're using the same language when it comes to describing variants. However, we did see 52 laboratories receiving deductions either for incorrect use or not using HGVS nomenclature at all. So that's 18% of labs. So we would definitely recommend that you do look into the correct application of the guidance, which is available on the website, or actually using HGVS nomenclature standardly and routinely within your laboratories. On the same basis, we also saw that some laboratories were only reporting the result at the amino acid level. Now, this is a big DNA-based test that is being performed. So we really would like to see the variants described in the terms of the nucleic acid changes, with the predicted amino acid change also being provided. But I think that's the key word there. It's a predicted amino acid change. So just to report it at the amino acid level isn't really in reporting the actual test that has been performed. Now, we're aware that some of the commercial kits report the results only at the amino acid level, but we know it is possible to determine what those nucleic acid changes, so the nucleotide changes, are from the variants using literature that's already with the kit, or databases or online tools such as Cosmic. So we don't think that's a reason for not reporting it at the DNA level. Alternatively, we know that some commercial kits don't actually distinguish between the nucleotide changes. So if this is the case for the kit or the assay that you're using, then the report should clearly state that it is not possible to characterize the variant any further. So that's the first observation we wanted to highlight. So if we move on to the second slide, please. The second one is about reference sequences. So again, this is something that we've been very strict and expecting on reports, molecular testing reports over the years. And we've seen sort of an evolution of the different types of reference sequences can be used. But here we're seeing that many, many more laboratories are now as routinely using reference sequences on the reports, which is great to see. However, we are seeing multiple reference sequences often being stated on a report, which is confusing because they can actually be different sequences, different transcripts, etc. So the clear message is that the report should state only one, the relevant one to your nomenclature reference sequence per gene on a report. So both EQA providers support the use of main select and main plus clinical sequences as denoted by the main initiative. And I think this is a way forward to help with the standardization, not only of to prevent misinterpretation of the results in a report, but also for variant annotation, interpretation, reporting, and database collation. So we very much support standardization using main sequences. We had previously been looking into and supporting the LRG reference sequences. That's still acceptable, but the RefSeq and ensemble transcripts really are specified by main, and that is now the preferred option. We had 37 laboratories, so just under the 13%, received deductions in this EQA for not including a reference sequence on the reports. So we're improving definitely, but we just ask those 13% of labs to use the appropriate reference sequence in the reports going forward. So next slide, please. And then the third and final observation that we see in many of our EQAs, but it really is quite critical when it comes to ctDNA testing in plasma, is about understanding the limit of detection of your assay. Now, we saw many laboratories continuing to not adequately report the limitation of their assays in their report submitted for the EQA. We also see a lot of variation of how the limitation of the assays are conveyed. So some are reporting the level or the percentage of ctDNA within the plasma sample, and reporting that either using copies per mil or a percentage. And it's very important to understand that these are not actually measuring the same thing. So the copies per mil is going to tell you the minimum number of copies of your DNA that your assay can detect. Whereas the percentage value indicates how sensitive the assay is at detecting that specific variant in your tumor DNA against the background of your wild type DNA. So it's very important that you understand what information you are actually giving on the report and what that truly means to the reader of the report. So ideally, we want both values should be determined, and that should be through your own in-house validation and verification, not through a manufacturer's data set. And this should be determined prior to the introduction of the test into your routine clinical practice. So it's good laboratory practice, and it adheres to the ISO standards, that you have a robust validation and or verification processes in place before you start testing clinical samples. So next slide, please. Finally, it just comes to Simon and I to thank obviously the huge team of assessors that we now have a global spread from our assessment team as well. So thank you very much to those of you who many are on the call. Also to the internal teams within EMQN and GenQA, and specifically to Jenny, Emily and Mel, who really have started to run this massive scheme and has it evolved over the years. So thank you very much to those teams. Now, Simon, I think we have some time for some questions. Do you want to have a look?
I've had a look, Sandy. We do have time, and so I encourage you all to try and submit a few questions. We haven't got any questions at the moment. So I will just, I guess, pick up on a couple of things that we've covered today. So one of the things that we've covered today is the fact that this is still a relatively new type of test, and it's in a new and emerging field in molecular diagnostics for cancer. And some of the things that we're picking up and errors we're seeing in our EQAs are not what we call routine, but we see them quite frequently in newly developed and newly introduced tests. And Sandy's highlighted some of the common and shared learning from them. So how you define your assay performance is crucial to, and how you convey that is crucial to the reporting process, but also to making sure that your assay is performing well. But also the numbers of the types of errors we're seeing in terms of things like reference sequences. And I find it, Sandy, still find it unusual, I suppose, in the sense of we're seeing laboratories making these common errors like not including reference sequences, yet we see in all of our other well-established EQAs that laboratories have learned from that practice. And so why do you think we see this discontinuity between this new test, which is effectively just another test being done often in the same laboratory, and the reporting practices for established tests? Have you got any thoughts about that?
Yeah, I think it's about the spread of the different types of laboratories that perform liquid biopsy testing. I think we're seeing more laboratories doing this sort of biochemical laboratories or clinical chemistry labs are doing the testing, whereby they might not routinely have experience in other molecular techniques. So I think we're actually getting a different participant capture of laboratories who haven't got that previous experience. And I think it's the learnings, and hopefully that will improve in time. I think we've seen improvement over the last few years for the ctDNA EQA. So I think it's just going to take time, but I do think we've got a new area of laboratories coming into this field, just depending on the way labs are set up in different countries. My main concern is the number of false positives and false negatives we see. I mean, I think we see a lot more false positives in this scheme than we do in other, like the solid tumor testing. And I think that's just the nature of the sensitivity of what can be picked up, and maybe not the understanding of how critical it is to have clean workup benches, clean laboratory facilities when you're handling samples with such low levels of variance that you need to detect clinically. I don't know, what do you think about that?
No, I would agree with you entirely on that. I think that's I mean, for you participants dialing in, it's worth Sandi and I emphasising we do put a huge amount of thought into designing these EQA schemes. We don't just pull the genotypes off out of thin air, and we certainly don't pull the variant allele frequencies we use out of thin air. You know, and in our pilot schemes, we did try to go down very low for some of these variants, and we realised that the testing process wasn't well set up in many laboratories for lots of different reasons we've highlighted in previous years and today. So, you know, when we think about providing you with samples here, we're thinking very carefully about what you're providing, the variants and the variant allele frequencies, and trying to replicate normal life, but at the same time making sure that most laboratories can still participate and hopefully get a result from it. So a lot of work goes into that planning process. But you're right, Sandi. I mean, I think the false positive rate is predictable in many ways. And I'm sure will improve over time, but you've seen the huge variety of different assays used by laboratories. And so it's impossible, I suppose, really to get away from the fact we will pick up false positive results because of the level of sensitivity laboratories are having to go to detect variants in this type of sample.
And as you say, it's also we've asked, a lot of people ask, why don't you have variant allelic frequencies of very, very low, so you can actually push the labs to determine what their limits are. And I think we tried that in some of the early pilot runs, but when a laboratory can't detect it due to numerous reasons, it doesn't actually help them very much in establishing their EQA and, you know, measuring the quality of this assessment. So we sort of reviewed and took stock of what the purpose of the EQA was for. And I think that it's really the responsibility of the laboratory to know what their limit of detection is. And it's more about EQA to measure what their clinical service actually can do. Would you agree with that?
I would agree entirely with that. And it's also worth, and we have a question based around limited detection. It's worth reiterating that there is already quite good and well-established guidance on test validation and how you might determine these specific parameters. If you are interested, that we can make that publications available on test validation and verification if necessary for laboratories that are interested in it. Another question we have, Sandi, is really regarding errors reported in the detection of EGFR and KRAS mutations ctDNA. Do you have any data on the type of test used for assessing the mutational status?
With regard to the errors, oh, everybody likes to ask this question, don't they? We do have the data, but it doesn't actually indicate that there's one particular method that is suboptimal to the others. You also have to remember that it's not just the testing methodology, it's also the sample handling, it's the extraction process and everything else that goes on within that whole end-to-end pathway for testing and reporting the sample. And it's incredible how individual laboratories can be using exactly the same assay, but there's so many little variations within the daily practice in the laboratories that just bring those different variables into the whole equation there. So there's no clear data to support that any particular methodologies or commercial assays are better or poorer than others. We just see huge variation.
Yeah, I would agree entirely. And I'd also say we GenQA and EMQN are very careful about that's why we're very careful in our reporting processes not to draw conclusions about assay failures or which test works better than others, because often we cannot tell what the cause of the error is and why laboratories made a mistake. I mean, you can see from the results we had cases 1 and 3, one laboratory mixed up samples, but we can't tell whether they mixed the samples up at sample reception, or they mixed up the reporting process, or they just didn't type the results in correctly into the results submission site. So, you know, I think you have to be careful to not overinterpret the findings from these types of assays. But it is also true to say we do find systematic errors with various assays, and that they're actually few and far between from a perspective of an EQA, but we do pick them up, and where we do pick them up, we will go back to the manufacturer and, if necessary, the regulatory body to highlight that error, and we will work with them to try and make sure that the assay is improved. So it does happen, but it's not very common. And as Sandi demonstrated, it's a huge variety of different assays used in this type of test. There's no common themes apart from the 3 ones we pulled out and the rising numbers of LDT, NGS types of assay.
And I think it's what we feed back to the regulatory bodies at MHRA in the UK, but they also have a network of their equivalent partners in different countries, so that it isn't just a UK specific initiative, it is actually global, and we do have that wide reach. Yeah. I think one of the other questions, Simon, that's in as probably could be taken another way about, do we recommend specific values regarding limits of detection? So rather than how to actually define them, is what should be used. So my thoughts around that is really you need to speak to your own local clinical teams as to understand how sensitive your assay needs to be to actually for their clinical practice. Do you need something that's incredibly sensitive wherein your clinical teams would not act upon it until it was much a higher level, or you could actually see progression on, you know, imaging, etc. So I would recommend you speak to your service users to define what assay or service that they're expecting, and you can then tailor the methodology to meet that need.
Yeah, I'd also add, I think it's a hot potato, that really, isn't it, in this field, testing field, and obviously there isn't a huge amount of guidance out there either about how low you really need to go. So yeah, I think Sandi's perspective is probably the way to take it, is to talk to your clinicians and understand what their needs are, and then adapt your methodology according to your local needs. Okay. Sandi, I don't think we've got any more questions, and I think we've the two of us have bounced some ideas between ourselves and answered a couple of the questions that have come through. So, shall we draw a conclusion to today's webinar?
I think so, and I think maybe just advertise the fact that it's running again in 2023, and we're also both in a collaboration looking at adding another EQA, a pilot EQA, and looking at multiple biomarkers as well in ctDNA testing. So there's definitely an evolution of this type of testing, and we're there in the forefront helping with standardization. So yes,
absolutely. Well, thank you to all of you who have dialed in. It's really appreciated that you've taken the time to listen to Sandi and myself this afternoon. We hope that we provided you with an informative and enlightening webinar on what we've done in 2022, and we look forward to you joining us in 2023. So it just leaves me to thank you for dialing in, as I said before, to thank, as always, my co-chair Sandi for all her contribution as well, to thank AstraZeneca for supporting this webinar and publicising it, and we wish you a good rest of the afternoon, and we'll look forward to joining us in future. Take care.
Thanks.
Thanks for now. Bye for now.